All right, here we go. All right, so this video, we're going to talk about naming ionic compounds using the transition metals. And that's a little bit harder than naming and writing formulas for ionic compounds from the tall groups, all right? Now, if we look over here at the tall groups, we know that all of these atoms have a +1 oxidation number. They lose one valence electron. These are +2, +3, plus or minus 4, -3, -2, -1. But these guys in the middle, we're about to find out why they're called the transition metals, okay? And the deal is, these bad boys right here, they don't have a fixed valence, okay? We don't know really what their Bohr models look like because there are multiple Bohr models for the exact same atom, okay? And that's frustrating. With the exception of aluminum right here, and if you go down from aluminum, you have zinc, and then right here we have silver, okay? And then over here under aluminum we have gallium. So these guys right here, okay, they make kind of a funky little Y. Those guys right there, they have a fixed valence. And this is something that unfortunately you will just have to memorize. And you can write this down in your notebook, probably a good idea. Silver is always a +1. Zinc is always +2. And these two guys are just exactly what you would think they were because they're under +3. They're always +3. All right? Now, if I'm drawing the steps here, the stairs, if I draw the stairs, all these other guys that are under the stairs or to the left of the stairs, all of those have multiple versions of their atoms. These are all the transition metals, okay? These guys right here are the only ones that aren't in these two tall rows that have a permanent oxidation number, a fixed valence. So let me show you what I'm talking about. Let's talk about scandium right here. Everybody, scandium is in position 3D1. Everybody agree with that? All right. So we're going to take a look at why scandium is a transition metal. Here is a Bohr model of scandium. 2, 8, 9, and 2. 2, 8, 9, 2. Now the reason it's 9 is because, remember, when we had these two on the outside, right, of the Bohr model. 1, 2. Then when we get to the middle, we start adding these one ring in. Does everybody remember that? Okay. So when we go over here, the last electron we add goes in a row, and it makes it 2, 8, 9, and 2. Okay? Now look at this Bohr model, people at home and people here in the real world. Look at this Bohr model and tell me what you think the oxidation number of this atom would be. +2. This would be what scandium +2 looks like. And that's right. That's what scandium +2 looks like. If you saw a Bohr model of scandium and it looked like this, it would be +2. But you know what happens sometimes with a transition metal? And this is what you need to watch. This is what you need to watch. Here's what happens with transition metals. Sometimes this outer electron can squeeze down in here and be an extra D. And you'd have 2 8, 10, and 1. That happens. And guess what that will make? Scandium plus 1. So that atom of scandium exists. Sometimes one of those extra Ds can be out here. And you could have 2, 8, 7, and 3. And that will be, see those 3 valence electrons now? And that will be scandium plus 3. Now, don't panic. I'm not going to make you draw Bohr models. I'm going to say, what's the Bohr model for scandium plus 3? And you might go, oh, God. I'm not making you do that. That'd be an easy question in college, right? But I'm just showing you that this happens. The D's and S's sometimes go in and out. So scandium is a transition metal. Now, all that means to you is that you have to name it correctly. So check this out. Here is the name of this formula. Ready? SCO. That is not scandium oxide. You cannot say that. You can't say, hey, the name of that's scandium oxide. Because there are multiple versions of scandium oxide. Look, this is scandium oxide. This right here is also scandium oxide, SC2O. So you can't say scandium oxide. The name of this one, hey, take a look at this formula, and you really need to be on it right now. Take a look at this formula and tell me, you know the oxidation number of this scandium because it's canceling out an oxygen. You know the oxidation number of oxygen. What's the oxidation number of oxygen? -2. So if there's only one of these canceling it out, what must that scandium be? +2. You always got to say minus and plus. So the name of this, if you saw this formula, SCO, then you would have to write on your paper, scandium 2 in Roman numerals in parentheses, oxide. Scandium 2 oxide. Does that make sense? Now, let's look at this one. What do you think the name of that one would be? If this one's called scandium 2 oxide, because you know there's a +2 charge here, what do you think the charge on that atom was if it takes 2 of them to cancel out oxygen? What must the charge on this atom be? That's right, Hayden. This one has to have been a +1 because it took 2 of them to bond with that one oxygen. So what do you think the name of this one is, Hayden? What's the name of it? It's called scandium 1 oxide. So you would write this. You would write scandium, and then you put a 1 in Roman numerals in parentheses, lower, smaller down here, oxide. Scandium 1 oxide. Or it doesn't necessarily have to be small like this. It just has to be after the word. Okay? It doesn't have to be a subfont, a subscript. Okay? Scandium 2 oxide and scandium 1 oxide. Let's try another one. And I'm going to explain to you why this is. Remember, these transition metals, these guys in the middle of the periodic table, all of these guys, with the exception of these guys right here, okay? All of these guys in the middle, not the tall rows, in the middle here, to the left of the stairs, all these guys have multiple Bohr models. They have multiple atoms. So, one of those examples is copper. Copper is a transition metal. If I were in the, and this is true, we have it back there. If I were in the chemistry back room with Mr. Jeffcoat and we were making up some chemical compounds, some solutions to use in class, which we do, and I said, Mr. Jeffcoat, hand me the copper oxide. A, he would look at me with a weird face because that's wrong. And B, since he's nice, he would just say, which one? Because we have this. We have Cu2O powder in a bottle, and we also have CuO in a bottle back there, a powder. They're two different things. They're both copper oxides, but you can't call it copper oxide because there's more versions of it. Does that make sense? You have to be specific. This one, it takes two of these atoms to cancel out an oxygen. So they both, if an oxygen has 6 valence electrons, each one of these has to lose how many electrons? 1. So if you see a formula that says Cu2O, then that one was copper, Roman numeral 1, oxide. Okay? And here's another way you can do this. You look at the formula. Oxygen's -2, you know that. That's where that 2 came from. So what must have been here? A 1. So you can just do that backwards if that makes you feel better. Does that make sense? Is everybody with me? So that's copper 1 oxide. Now that we've been doing this, Zach, what's the name of this one? That's copper 2 oxide. Excellent. Good job. If we look here, it's CuO. Every oxygen's -2. You know that. It's got a permanent valence. So this one had to have been a +2 to cancel it out, right? So that's copper 2, that means 2 I's, oxide. Here are some Roman numerals for those of you at home who might not remember. 1, 2, 3, 4, 5, 6, right? That's knowledge you came in here with. And I don't think you'll have anything higher than 6. So many atoms on the periodic table have multiple Bohr models. Those are the transition metals, and that's why they're really called the transition metals. Okay? So now we can do it the other way. Very simply, I could write down a name, and then you can give me the formula. How about this one? Titanium 3 oxide. Write the formula for that real quick. Titanium 3 oxide. Okay, titanium 3 oxide. We're going to go ahead and do that one first. All right. Titanium 3 oxide. Titanium 3 oxide, that means we would say titanium, and we would write +3, because that's what the 3 stands for. The Roman numeral is the charge, right? Right? Oxygen. We know the oxygen was -2. What do we do with these numbers, Sam? Cross them down. Put the 2 there, put the 3 there. Ti2O3. Good job. Let's try the other one. Try that next one right there. The next one says cobalt 1 nitride. Cobalt 1 nitride. cobalt 1 nitride? I'll give you a second on that. All right. There's a symbol for cobalt. There's the symbol for nitrogen or nitride. What does cobalt 1 mean, Sullivan? Cobalt 1, what does this 1 stand for? It's the charge, the oxidation number, right? Stands for +1. What do we know the charge for nitrogen is, Drew? -3. What do we do with those two numbers? Cross them down. It would take 3 cobalt 1s to cancel out a nitrogen. So the formula for cobalt 1 nitride is CO3N. Here's the last thing I'm going to say about it. Don't do this. 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 Now I've told you 10 times. That's what my dad used to do. I'm kidding. All right. Here's something I see happen all the time with students. They'll see this. Cu2O. Copper 2 oxide. Wrong. This isn't the Roman numeral. That's how many of these atoms there are. Right? You like instinctively, and it's not because you're stupid, it's just that's how our brains work. You go, oh, copper 2 oxide. No, this is copper 1 oxide. The 1 is the charge that was here. It takes 2 copper 1 atoms to hook up with 1 oxygen. So Cu2O is copper 1 oxide. Does that make sense? Rarely would this number and the Roman numeral be the same. Okay? I can't off the top of my head come up with one that would be the same. But do you understand? The Roman numeral is the charge.